Hi everyone, welcome to Differential Calculus. Today we explore lesson 4.7, Optimization Part 2, and do a few examples that doesn't require us to come up with the constraint equation. Example number 1, an open top box is to be made by cutting off each square corner of a square printer paper 10 by 10 inches and folding off the remaining sides on the end. How should you cut out each corner so that the box has the largest volume possible? Here comes the paper. We want to cut out corner X, 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 X. Cut in by X. Well, from here, we can figure out the volume of the box because the length is 10, right? And if we cut out X from each side, then we'll have a square in the middle, and this square, the side is 10 minus 2x. So when we fold it up, then the volume is base area 10 minus 2x square multiplied to the height x, and the objective is to maximize the volume. Volume is written in terms of x, so we don't need a constraint equation. From here, see that v prime is, well, this is the product of two functions. Use the product rule. 10 minus 2x square times 1 plus x times 2, 10 minus 2x times negative 2. We can factor out 10 minus 2x, and we'll have a 10 minus 2x minus 4x. So 10 minus 2x multiplied by 10 minus 6x. Set each factor to 0 because we're going to set the derivative to 0 to figure out the critical number. 10 minus 2x equals 0. 10 minus 6x equals to 0. So here we have x equal 5. And on the other side, x equal to 10 over 6. Or 5 over 3. Well, 10 equal 5 is not possible because we cannot cut in half of the paper. So not possible. Meaning that based on the restriction of the paper size, x is 5 over 3. And because that is the only critical number, hopefully it's gonna be the local maximum. Let's take a look at a test here. So, 5 over 3. Let's pick the v prime 1. Right? Plug in the number 1. You see that is the positive, and v prime of 2. If you plug in 2, it's negative. See? Increasing to decreasing. Yep, by have a local max F53. Yeah. So the local maximum is the absolute maximum because we only have one. And therefore, we have to cut 5.3 inches. An oil refinery is located on the north bank of a straight river that is 2 kilometers wide. A pipeline is to be constructed from the refinery to the storage tanks located on the south bank of the river, 6 kilometers east of the refinery. The cost of land pipe is $400,000 per kilometer over land to a point P on the north bank and 800,000 kilometers under the river to the tanks. To minimize the cost of the pipeline, where should P be located? Oh man, it's a nice problem. First, let's sketch out. So we have a refinery right here. And it runs along the north bank of the river to a point that is 6 kilometers. The river is 2 kilometers, and down here is the tank. We want to put the point P somewhere right here so that we can minimize the cost of, pipeline under the water. So we put the point P right there. Then this is X, and the distance right here is 6 minus X. Notice that this is a right triangle, so we can figure out the side of the hypotenuse. I'm gonna put using Pythagorean theorem. Let the side be D here. D square is X square plus 2 square. D is root of X square plus 4. The goal in this problem is to minimize the cost of the pipeline. So we minimize cost of the pipeline is the cost on the land. So on the land for this much distance here, and at a cost of $400,000 per kilometer, $400,000 times 6 minus X plus, well, it also cost us to go underwater for this much distance, and it is $800,000 per kilometer under the water. Let's find the derivative. Set it equal to 0. Figure out the critical number. Hopefully there's only one. Derivative is negative 400,000 plus 800,000 over 2 root of X squared plus 4 multiplied to the derivative of the inner function 2x. So 2 cancel out, and we can set this equal to 0 and solve for x. So what we have is 800,000 x over root of x squared plus 4 equal 400,000. Multiply both sides by root of x squared plus 4, then 800,000 x is 400,000 root of x squared plus 4 divide by 400,000. 2x equal root of x squared plus 4. Well, it is a radical function. Square both sides. 2x squared is x squared plus 4. 4x squared equal x squared plus 4. So we have a 4x squared minus x squared minus 4 equal to 0. 3x squared minus 4 equal to 0. So x squared is 4 over 3. X would be, it can only be a positive number. Root 4 over 3, which is 2 over root 3. Let's test out the only critical number. Hopefully it is a local minimum. This is 2 over root 3. So pick f prime up 1, or in this case c prime 1. Plug into the derivative function and then say that, oh, it is less than 0. Pick c prime up 2. One, two, three. Let's test out the only critical number to see if it is a local min or local max. We use the first derivative test. 2 over root 3. C prime of 1. 2 over root 3 is a little bit more than 1. So C prime 1. Plug it in, less than 0. On the right side, C prime of 2. Oh, plug in, it's more than 0. So decreasing, increasing. Yay! We have a local minimum f of 2 over root 3. Well, we don't have one local minimum, so it is the absolute minimum. Therefore, the point P must be located at 6 minus 2 over root 3 kilometer east of the refinery to minimize the cost of the pipeline. Thank you for watching. I hope you found the content useful. I'll see you in the next video.